So welcome to our session on IPv6 and IoT. So this is a final session, of course, of Cisco Live. It's always a concern when you're the very last speaker of the show because everyone's thinking about doing some sightseeing before they fly home. But the people that come are the ones that are actually very interested in the subject. So I'm very glad you're here, and I hope this can be a good experience for you. So my name is Robert Barton. I'm a principal systems engineer, and I'm based in Canada. I'm from the city of Vancouver. It's on the west coast of Canada. So I'm delighted to be here in Europe to talk to you about the subject of IoT. It's a subject I've worked in for a long time and have had a hand in developing some of the largest IoT networks that we have deployed at Cisco, and of course, most of them have been IPv6 based. So we're going through a massive technological change in the world right now. Things are becoming digitized at an increasing rate. Everything from lights in the ceiling, to sensors in the grocery store, to embedded sensors on the road. Everything is starting to be connected to generate information, and we're starting to use that information. So we call this technological shift the Internet of Things. But the question is, how do you build an architecture for something so different and so big? Well, we're going to discuss how IPv6 is really a foundational element for this modern change of digitization and IoT. But IPv6 is a rich protocol, but it still has some changes that it needs to make, some modifications to really let it fit well into IoT. So we'll look at what those adaptations are, including a new routing protocol that was developed specifically for IPv6 and IoT. I'm going to give you a little glimpse into the future, what's coming with something called time-sensitive networking, specifically adapted for IoT applications. And then I'm going to give you a case study at the very end. And it's a very exciting one because it's the largest IoT deployment that Cisco has ever done. And it is all IPv6 based, and it is in my hometown. So it's something that I've had a chance to be very connected with. I'd also like to hear questions. If you have some questions or comments that you'd like to ask during the session, please put up your hand and make some questions. We can share with the audience. Last year, I was involved in a project at Cisco to write a Cisco Press book on IoT. And actually, the content in this presentation is very much based on that book. And we ended up filming a 15-hour video series on that subject. So Pearson Publishing actually gave me 2 free coupons to hand out to the audience. So I'm going to give this to the first 2 questions that are raised. And this is worth $300 US is what they're selling it for as a list price. So first 2 questions, it has to be good questions, not like, when is this going to be over? And what's your name again? So if it's a real question, then I'll be very happy to give out these coupons to anyone in the audience. Okay, so how does IPv6 fit into the world of IoT? So I want you to imagine for a second that you're not a network engineer, but you're an architect. And you're a very good architect. For your whole career, you've been building homes, beautiful mansions. You're skilled. You're the pinnacle of your skills and ability, and you're recognized for that. But then one day, the president of the company walks in and he says, we have great news. We've just won a new contract, and I want you to lead this new architectural design, and guess what it's going to be? It's the new Olympic Stadium in South Korea. Of course, the Olympics start next week. Well, you're thinking, oh my goodness, this is a big contract, but I've only ever built houses. Maybe houses for 5 to 10 people, but nothing that can seat 60,000 people. This is a very different structure, used for a different purpose, made for different reasons, with different building materials, and the scale is so much bigger than anything I've ever done. That's an overwhelming feeling, to feel that you're so much of a fish out of water and being asked to build something on that scale. Well, that's how I felt the first time a first IoT project came along. For my whole career, it was about building enterprise networks. Now, of course, many people have built service provider networks, which are large scale, but IoT takes that even to a higher degree. You may have seen a diagram like this sometimes in the past, predicting the scale of connected things. And by 2020, it's predicted we'll have 50 billion objects connected and digitized in some shape or form. That's an enormous scale. And much of that is being driven by IoT. And this prediction was made actually many years ago. It's been updated, but it's still on track. The prediction is actually very, very accurate that by 2020, we will have 50 billion connected devices. Can you connect 50 billion devices with IPv4?
With NAT, yes.
With NAT you can, but it would be very hard to manage. It's so much easier with IPv6. But we have to build an architecture for it. We cannot use the exact same methodology and the same techniques we use in building enterprise networks or even service provider networks when it comes to IoT. The applications we use in IoT are different than what people use in the office, and they're different than what service providers typically give to their customers. We're using different materials. These are wireless sensor networks that run on different protocols. We don't use these protocols in typical enterprise networks, for the most part. So we have to think a little bit differently about this architectural shift. Now, a lot of this has been driven by consolidation of networks. So we see convergence towards Ethernet and towards IP. Now, that's not a new story, is it? We've seen this for many years. Back in the late 1990s, telephone systems with PBXs started to go away, and they converged into IP-based phone systems. Of course, IP version 4 mostly, but still it was a consolidation. And over time, more and more technologies have consolidated down to Ethernet and IP. For example, coax for video surveillance systems are primarily Ethernet-based today. Who knows what BACnet is? Okay, BACnet is a protocol used in building automation systems. So HVAC controls, things that are sensors on the walls for CO2 sensors, thermostats. There is a standard in the industry called BACnet that connects those. That has all become part of Ethernet. These are all converging onto the same switching infrastructure, but they're IoT. We're seeing lighting, ventilation, and more things are consolidating down. Now, while you could try to continue building this with IP version 4, the manageability is difficult, and it's just so much easier with V6. Now, one interesting example I wanted to share with you from back home, but this is something that's happening worldwide, is lighting. Now, it's very obvious why LED lights are better than traditional fluorescents or halogens or other type of lights. There's a cost savings. The lights almost never burn out. You can run LED lights for 20 years. And yet, there's a cost savings when you install them. When you put these types of light in the ceiling, what type of electrical cabling do you need? It has to be plenum-rated, very protected wiring. That's very expensive. You need to pay an electrician to put those lights in. But if it's an LED light, guess what? You can power them with a PoE switch. So 3 years ago, in our Canadian head office in Toronto, we moved into a brand new building, and we worked with the landlord, and he agreed to put in PoE lighting powered by Cisco Catalyst switches throughout the entire floor. Now, what's more than that, we have 4 floors in this building. They actually decided that the entire HVAC system within this building would be Ethernet connected. It ended up being 2,200 ports for the HVAC system running on BACnet. This is a big IoT network within a building automation. Now, people are sometimes surprised when they come in the office, they're looking, hey, where's the light switch? Well, guess where the light switch is? It's on an app on your phone. Now, some rooms have it because they got so confused. We actually had to put a light switch in. But a lot of light switches are actually on your phone. But the phone is more than a light switch. It can change the color of the lights, the intensity of the lights. You have this digitization capability now because it's an IP device. Well, how many ports would you use in the ceiling versus on the floor? And I think this really surprised us. When you see how many ports you start to deploy for LAN switching, most people are going wireless these days, aren't they? But in the ceiling, it's like a 5 or 6 to 1 ratio of ports you're going to use up there. Each one of those will consume an IP address. Here's an example of one of the lights in the ceiling. These lights actually have sensors as well to detect occupancy. So you start to use these for real estate purposes. You understand, well, there's a person underneath this light, so that floor space is being used, and we can justify that floor space and the rent we have to pay. Well, how do you build out this type of network? You put in specialized switches. So there's these switches called the DBS8, the digital building switch with 8 ports of PoE. It actually straps up into the ceiling. It's fanless, so it makes no noise. And it simply hands out IP addresses to the lights, and then we have full manageability. Now, these are interesting switches, and they had a good demonstration at the World of Solutions with our digital lighting and digital ceiling examples. They have something called perpetual PoE, which is very cool. It means you can actually do a software upgrade on the switch and reboot it, and you never lose power to the lights. It'd be a bit frightening if someone was deciding to do a code upgrade because there was a security vulnerability and all the lights go out. Right? That'd be a very bad thing. We wouldn't want that. So these switches support PoE, and we don't really care what lighting vendor it is, whether it's Philips or Cree or Molex. As long as they support Power over Ethernet and IPv6, then we can support that type of a light. And I'll give you an example why V6 is so easy to use and adaptable. Who's familiar with Slack, right? Stateless auto configuration. Well, all you simply have to do is on the router connected to the switch, allow the addresses to be handed off locally, and simply give it the DNS entry of where the DNS server is, so that the light can then get its address, register with the lighting controller, find the mothership, essentially, and then you have full connectivity to that light. So we put 1,400 lights with IPv6 within our 4 floors of the Toronto office. The number of lights was about 5 to 1 the number of people that were actually in the office. But it made it so much easier to deploy and much quicker than it would have been in any other type of way. Oh, question. Oh.
Maybe it's not good.
Oh, hold on.
So what is the advantage between IPv6 and, for example, Zigbee?
Okay, so the question is, what is the advantage between IPv6 and Zigbee? And I think that's a good question, actually, because we're going to talk about Zigbee a lot in this presentation. It's coming up in a few minutes. And Zigbee as well, it's a layer 2, and it's an IEEE 802.15 protocol. We're going to use IPv6 in Zigbee, and you're going to see how that happens in just a few minutes. And I liked your question, so here you go. Okay. So when we're building IoT architectures, we need to think about a methodology. How do we put this together using IPv6 and connecting it back to the IPv4 network, which is probably not going to change too quickly, but then address the applications that are running in IoT. And you find that IoT is a very data-centric type of a network, because the data that's being generated by these devices, it's what you care about. The data is what lets you interpret what's happening in the network to make changes, to become more intelligent and improve the business. Now, there's a lot of architectural models for IoT that have been developed. Gartner has a great model. The One M2M Alliance has a great model. One of the earliest and still most referenced is something published by the IoT World Forum, which Cisco is a part of along with IBM and other companies. And they've developed a 7-layer model. Now, we like 7-layer models, but it has nothing to do with the OSI stack. But as you can see at the bottom, it's the physical things. These are the devices that you might connect with Zigbee or Wi-Fi or PLC or other type of technologies. But as you go up this connectivity and then you have your data abstraction layers, you get into the cloud and the data center where you start to pull the data together. What I find useful about this model, it allows you to clearly separate where is your IPv4 network and your IPv6 network. Now, as we're deploying these large greenfield IoT networks, most of the things below is where the v6 is going to be. But IPv4 is still going to remain within the IT organization. So you need to have either dual stacking or you have some kind of connectivity between the two systems. What we see below here is what we call operational technology, or OT. And if you're familiar with IoT, OT is one of the most common expressions that will be used. It's the same as like IT is for the network running in the IT organization. So IT and OT are usually run by very different groups. But we have to start talking with each other and collaborating and bringing the systems together. So as we get into this architecture, we're going to look a little bit on the OT side and see how is this IPv6 network built up. Okay, so IPv6 really does lay a foundation for many types of IoT, whether it's in transportation systems, smart connected cities, building automation, smart grid, smart meter systems, you name it, IPv6 is a very good choice. And the reason is, for number one, the scale. So it can handle the massive scale very easily because of the address space. You don't have to worry about getting into NAT and private address space and address reuse. We also are able to support this convergence of IT and OT, which is an incredibly important thing because you need to have a clean separation but also merger between the two for management. It gives us nice interoperability. Because IP is an open standard, anybody can build a stack, drivers, and connect these other things, if they're making them, into your network. It's also very simple to manage from an address point of view. And of course, IPv6 has some built-in security capabilities. So all in all, it really does form the foundation for IoT today and going into the future. But the biggest problem that it solves is the one that everyone's working on. So when you think about IoT, what is the biggest challenge? It's the heterogeneity of IoT objects and their protocols. When you think about Zigbee or Wi-Fi, these are different protocols. They don't talk to each other. We think about RFID or 3GPP, which is a cellular narrowband IoT protocols. These natively do not communicate together. But as we deploy big IoT systems, we want them to actually be able to communicate. If I put a sensor on the wall to measure the temperature or the CO2, and it was a wireless sensor, and was using like narrowband IoT cellular or Sigfox or LoRa or something similar, I would want it to be able to talk to my backnet system for HVAC control, wouldn't I? Well, natively, those two systems don't really communicate. They're different types of protocol. But because IPv6 is an open standard, if we use a network layer that allows this intercommunication, we can solve that heterogeneity problem. So when you look at the research and development that's happening in IoT, there's a tremendous amount of papers, research happening how to solve this, and a lot of it is at the IPv6 layer. Now, I just wanted to mention one thing as a level set for our audience. When people talk about IoT, there's typically two flavors of it. There's consumer-based IoT, which is things you have in your home, for example, Google Nest or Alexa, those types of things. That's sometimes an IPv6 network, but not typically. It doesn't need to be. But when we talk about industrial IoT, these are the very, very large systems. For example, connecting all the parking meters in a city the size of Paris or London or Amsterdam. How would you do that at scale? Like, that's industrial IoT. There's where we're going to see IPv6. So for reference in this presentation, what we're talking about is really the application towards industrial IoT. Okay, so IPv6 is a very rich, it's a very powerful protocol, and yet it wasn't designed for IoT, was it? It was designed with other things in mind, and IoT has sort of come very naturally later on. But when we look at IPv6, it's sort of hard to squeeze it into IoT for certain reasons. Well, think about the packet size. What's the MTU of an IPv6 packet? Who knows? Right? 1,280 bytes? It's a big packet. A lot of these IoT networks are very constrained. They run with very small packets, and you're taking a big IPv6 packet and trying to squish it into IoT. So this is a problem that had to be overcome, as well as routing protocols. Which routing protocol could you use for a network with 2 million devices? This is a much bigger scale than most routing protocols were ever designed for. How do we manage it? What type of management and service discovery mechanism should we use in IoT? Because the ones built for IPv6 are not natively built to support those IoT environments. So we're going to take a look at some of the standards that have been produced by particularly the IETF. A new routing protocol that's called Ripple. We're going to look at extensions to IPv6 where we manipulate the header through an adaptation layer. And some management protocols like CoAP and MQTT that are designed specifically for these sort of environments. So we'll discuss that first, and then we're going to get into a larger case study that brings all of these things together into a real-life example. Okay, so the first real massive IoT networks were built for the electrical power industry. This is called the smart grid, and primarily smart meter deployments. As the utility companies realized there was a real business case to swapping out their meters, they wanted to connect them with IPv6, and the protocol of choice was a variant of Zigbee called 802.15.4. That's actually what it's called. It's in the Zigbee family, but it's not exactly Zigbee. It uses a channel hopping sequence. It has low power. It's a fairly lossy type network, but it works really, really good at scale. Now, the engineers realized if we're going to use that type of a protocol, we have a fundamental problem, because the frame size, MTU, is 127 bytes. And here is IPv6 at 1,280. So how are we going to take this and squish it down? Right? We have 128-bit addressing in IPv6 for source and destination. You're going to consume so much of that frame size just with the IP addressing. We have to do something about it. Well, what they did is chopped it up into little bits called fragments. So fraglets, I should say. And this introduced the adaptation layer into IPv6. So you can think of this as sort of sitting between layer 2 and 3, a layer 2.5, where we're taking the existing IP layer at layer 3, and we're doing some modifications to the header, specifically for IoT environments. Now, for example, this is the top one, something called 6LoWPAN, or IPv6 for Low Power Wireless Personal Area Networks. It's the specific adaptation layer built for the Zigbee-type protocols. So with 127-byte frames, we chop up our packet into these little fraglets. Now, we're sending a whole bunch of them as sort of UDP-type packets instead of this big, long 1,280-byte packet. But then what is the efficiency within that packet? Well, it really goes down. If you look at the typical IPv6 header, it's a 40-byte header. That's twice of IPv4. If you look at extension headers with IPv6, it's going to get bigger, even up to 60-byte header. And then your payload gets really small. In fact, this is around a 40% efficiency if you're using a 127-byte frame. That means you have to send a lot of these fraglets to be able to produce data and send it across the network. It's not something we want to do. So what the engineers at the IETF did is with 6LoWPAN, they said, well, let's have a compressor on both ends at the sensor level and at the next hop, at the radio, compress the header from 40 bytes down to about 2 to 4 bytes. They're squishing it down really, really low. And what this does, it increases our payload from 53, more than double, up to 108 bytes. So our efficiency went from about 41% up to 84%. So using 6LoWPAN, what we've done is adapted IPv6 to work much better in an IoT environment. Now, this was developed about 5 years ago, and it was specifically built for this Zigbee-type protocol called 802.15.4. Now, it would be nice if we had the support in a lot of other types of protocols. Well, what about Bluetooth Low Energy, or DECnet, or Power Line Carrier, PLC, BACnet, as I mentioned, in building automation systems? So they realized that this was a very, very successful way to adapt V6 into IoT. So the strategy became to let's take 6LoWPAN and just call it 6Low for low power and lossy type networks. And we're going to try to do it for everything. So the IETF formed subgroups for almost all of these different types of technologies. And one of them has been ratified already, which is for Bluetooth Low Energy, and the others are continuing to work. So as you see with IoT, we're going to use V6, but we have to still mature a little bit more of the protocol to be able to squish it down into these smaller IoT lossy type frames. Now, one that's not on that list, which you might be wondering about, is a class of IoT access called low power wireless access, or LPWA. Who here has heard of Sigfox? Anybody know Sigfox? How about LoRaWAN? Okay, so some in the audience. This is a very, very fast emerging class of IoT access layer. It's quite amazing actually what it can do. The distance of, for example, LoRaWAN is, they say, between 15 and 80 kilometers. Think of the range. I actually have a colleague that works in Brussels, and his sensor was in Paris. And when the airplane got up over Brussels, he was able to receive signal from his sensors in Paris, some 300 kilometers away. Now, that's an incredible distance, and it really is because of the modulation that LoRaWAN uses. Now, there's competing technologies here. LoRaWAN is one, Sigfox is another. But industries are starting to realize we can use these everywhere. We can put these into fire hydrants to realize when the fire hydrant springs a leak and the pressure goes down. We can put this into garbage cans all over our city, and when the garbage can starts to fill up at a certain level through sensing of the height of the garbage, we can send the truck to go pick it up. We don't have to send the truck and pick up the garbage can when it's empty, right? We put a little cheap LoRa sensor that's only $5, and we can put them all over the entire city. And because of the range, these LoRa radios can cover the city with maybe 20 or fewer radios. So the potential of LoRa and Sigfox is fairly incredible. Yeah, there's a question.
Yeah, but when you told us that we can cover big distances, how about the frequency space? Is this regulated?
Okay.
Because we will end up in some whatever situation with many devices.
Okay, so the question is, what about the frequency space? So both Sigfox and LoRa use unlicensed spectrum in the ISM band. Now, that, of course, is a problem if you have interference. But the way the architecture works is because they use so many radios spread out, they all receive a copy of the signal, and they rebuild and reconstruct the signal. Even if there was a tremendous amount of interference, it actually still is able to work. LoRa networks scale to hundreds of thousands of nodes. Now, the other side of that coin is licensed spectrum. So the cellular companies have adopted a standard called narrowband IoT, which is part of the 5G suite of technologies. So if you follow 3GPP, that would be a competitor using licensed spectrum. Now, it's going to have more bandwidth, it's going to be faster, but you're also going to pay for it because licensed spectrum is not free. So we're seeing this rapidly develop, but if a company wants to have control over their own IoT network and put this in, it's very simple to put in a LoRa network or a Sigfox-type network. Now, Sigfox is our competitor. We don't sell Sigfox. LoRa is part of the Cisco technology. Pass this to you for your excellent question. Thank you. But because it's such low bandwidth, it's incredibly low bandwidth. We're talking not megabits per second. We're barely talking kilobits per second. It's only 5 kilobits per second at maximum speed. As you get further away, the modulation changes into something called a spreading factor. We get down to 290 bits per second, right? This is a very, very small amount of data. But if it's a parking sensor to see if there's a car parked in a spot, you don't need to push a lot of data. It's either the car is here or there's no car here. That's all you really have to worry about. And if you're talking about Sigfox as a competitor, the maximum throughput is 100 bits per second. It's even less with a very, very narrow 200 kilohertz channel. So these are incredibly interesting and powerful IoT access technologies, and they're growing very, very fast, especially in Europe. Europe has really been the early adopter for both of these technologies. North America has started to adopt it, but much more slowly. But what's interesting is when we look at these technologies and you look at the protocol stack within them, there's something missing. Do you notice this protocol stack? We have our unlicensed spectrum, so 868 megahertz in the European Union. But then you get into the layer 1 modulation, and then you skip to the MAC layer. And what's above the MAC layer? The application layer. What do we usually have between these two layers? Network layer, right? Where's the IP layer in the LoRaWAN stack? Well, there's no IP layer because the bandwidth is so constrained, it's so small. The engineers realized that there's no way we can actually fit in IP, let alone IPv6, so they completely dropped it. And in fact, if you look at the architecture of a LoRa network, you see the sensors and devices down here. You have an array of gateways that receive the signal and reconstruct it. But then you have a LoRa network server which sits up in the cloud. The layer 2 adjacency is from the server all the way to the sensor. There's no IP routing that happens. This is all tunneled. And then you have an API which serves off the application. They had to make it really a star topology because of the lack of an IP layer. Now, it works today. It actually is in production all over Europe, starting to be in North America. But architecturally, we're missing IP. So the engineers at the IETF have realized if we can add IPv6 to this, we can solve a huge problem. We don't have to terminate our MAC layer from the sensor to the network server. So the IETF is working very, very hard, and they're not yet ratified, but they're proposing a very, very highly compressed version of 6LoW, pushing this down into the LoRaWAN stack and the Sigfox stack, so it'll be across all LPWA technologies, and allow us to bring IPv6 into this technology space. So this is a little bit of the future. We haven't seen this actually deployed yet, but this is the way that the industry is moving. Yeah, question?
But why do you use then the 6 and not the 4? Where's the advantage now of the 6? Because you can even compress 4 even more, and you have to, if you go one slide back, you have the gateway anyway, which is speaking 4 or 6 or whatever.
Yeah, thanks for the question. So the question is, why not use IPv4, which has a smaller header basically than v6? And the reason is that the intended scale of LoRa and Sigfox networks is much, much bigger. When you look at a smart city, like if you were to put one of these radios onto every parking meter into the city of London, how many would that be? That would be in the millions. If you put on every traffic sign in every intersection in the city of Paris, this would be hundreds of thousands. The scale is so much more massive than what you would design an IPv4 network for. You would run into all other kinds of problems.
But the addressing is the MAC anyway, what I understood. So from the gateway's perspective, you address the parking meters with their MAC.
Yeah, so the question is that we address them within that. This gateway is simply a pass-through. So he's not actually terminating anything. He's just simply bridging and passing through. So you do have a huge MAC table sitting on this LoRa network server, right? So that's where we start to hit scalability problems. It's just it will work much better and more fluidly with IPv6. But it's a good question. We can talk more maybe a little bit later. Yeah, thank you for that. Yeah. OK, so when we look at large-scale IoT networks, the question of routing has to come in. We know now how we can fit v6 into these constrained networks, but what protocol are you going to use? Is it ISIS? Is it OSPF or BGP? Well, early on, we looked at these problems that this is a very, very difficult problem to solve, because a lot of IoT networks are actually mesh networks. I showed the example of LPWA that's a star topology. That's more unusual in IoT. We often see mesh-type networks where nodes interconnect with each other and eventually find their way to a root. Over time, they realized there's no protocol out there which actually works that well. We need to go back and invent a new protocol. And the result of that work, the IETF, was something called ROLL, or Routing Over Low Power Lossy Networks. This eventually emerged as RFC 6550, and now we just call it Ripple. It's a nice name, Ripple. It has nothing to do with RIP, if you're familiar with RIP. Is anyone here old enough to remember RIP? I remember doing RIP on my CCIE exam, and if you're using RIP today, we'll talk later, okay? But hopefully you're not using RIP. This has nothing to do with old classic RIP. It is a distance vector protocol, however. But the idea of Ripple is that it's built for a very lossy network. So if I'm transmitting a bunch of data, I might be losing 50% of my packets because I'm in unlicensed spectrum and because it's a very, very congested environment. It's built to handle those types of situations. The thing about Ripple that makes it special, though, that really is unique, is its adaptability for different objective functions. Objective function is the algorithm you use to route. And because IoT environments are sometimes very difficult, you have interference, you have buildings in the way, you have different problems, you need a more adaptable algorithm how you're going to route through your network. So Ripple emerged primarily related to the Zigbee variant of 802.15.4, but today we see it really become the routing protocol for IoT. And it's only built for IPv6. It does not work on IPv4. Ripple is really taken from this concept of a graph. So if we look back to the mathematical introduction of graph theory, there's a mathematician named Euler, which really is the founder of graph theory. And the idea is that you have nodes. Oops, I'm going the wrong way. You have nodes, and you have adjacencies between nodes. And if you want to find your way to a destination, you really have to find a series of nodes and adjacencies to get there. So you build your path through a graph to find your destination. Now, a classic graph like this is called a DAG, or a directed acyclic graph. In a network, we're typically finding our way to a router up here, which is a gateway between our IoT mesh system and the rest of the network. So this is called a direction-oriented DAG, or a DODAG. It's a really funny name. Every time I say it, people are like, what are you, crazy? What's a DODAG? But this is actually the mathematical term for a graph where you're pointing to a particular direction. The top of this graph is the router, right? This would be our IPv6 router that serves as the root for all of this tree. Now, below here is a mesh. So all of these nodes are sensors. They could be meters. They could be different IoT devices in a factory that communicate to machines. All of these form connections with each other, eventually finding their way to the root. Now, here's an example of an actual system. You have a root here. And I use an example of a grid router. This is the Ripple mesh down below, and it forms a tree. At every level, we form a rank. A rank is really how deep you are into this mesh. So we have rank 1, rank 2, rank 3, and we use the ranking to basically prevent loops. So if you're at rank 3 and you go to rank 2, you should never go back to rank 3, because that could indicate you're going through a loop in the system. Now, from a routing perspective, what do we need to know? We need to know how to find our way back to the root. Essentially, that's like finding our default route back out of the system. So the root here advertises himself through something called a DIO, or DAG Information Object, basically saying, I'm the default route to get out of your mesh. Come towards me, and you can find your way. Well, all of these guys down below, they also need to know the structure of this tree. So they advertise themselves out, and they start to build their topology so they understand who else is in this mesh. So if I need to go from this guy over to that guy because he has a resource I need to also have that topology information. So they advertise information about themselves using a DAO, so DAG Advertisement Object. These are IPv6 advertisements of really their position within this tree, and it allows everyone to build the routing table. So here's a show WPAN Ripple tree. This is very similar to a show IP route of another routing protocol, and this is from a live mesh network. The very top is the root, so here is this v6 address. This is the root of our tree. The first indentation would be rank 1, so he's sitting at 1 level below. And then we have, from here, there's 4 children sitting below him. This is the structure of our tree. Yes, question? Mm-hmm. Okay, yeah, I understand, yeah. So excellent question. So the question is, are we looking at integrating Ripple into a more classic routing protocol? And actually we do. So the way this is deployed, on the mesh side of the network, this is the only routing protocol that's going to work. Not only does it do discovery, but it builds the topology of our tree. However, when we get to the root, that router at the top, we go through a redistribution process. So we will redistribute to OSPF or ISIS or something more stable like BGP, but you do have redistribution points where these network addresses are learned on both sides. Okay, good question. So here's an example of the routing table. Now, the way the tree forms is the most interesting part. Do you remember I said objective function? That's the algorithm we use to really find and build this tree. The objective function really is a decision criteria how we're going to find a parent. So let's say a new sensor comes on and he wants to find his position in the tree. And he says, well, there's a whole bunch of candidate parents that I could connect to. We're using the routing protocol's algorithm to decide which parent that we're going to connect to. Question?
Is it really a routing protocol or is it based on layer 2? So it's more or less a layer 2 adjacent.
Okay, so the question is it really a routing protocol? It actually is really a routing protocol. So it is a layer 3 routing protocol, but it's not the type that we're used to, like ISIS or OSPF. It works in more conjunction and with an understanding of layer 2. Right? So it works fundamentally a bit different. Okay? So in this case, we just say, well, how am I going to figure out my routes? I could look at something called ETX, and this is the most popular objective function. ETX is a measurement of how reliable my link is. So if I want to, let's say this front row, let's say 4 of you guys are my potential parents. Who am I going to connect to? Well, let's say I send a text message to all of you. I send 5 text messages. If you all send me back 5 text messages, that means, oh, this is very reliable. I can take my pick. But if one of you doesn't send back, that would be bad. That's my ETX, my expected transmission. It's a measurement of how reliable my connection is. So what he does is he sends some packets, and he looks at how many acknowledgments he gets back. If he gets all of his acknowledgments back, the ETX is a very low value. Lower is better. It's a 1, and he says, that's the guy I'm going to connect to. But I could also do an objective function based on my hop count or my measured latency through the network. I want to go with the lowest latency parent. I'll choose that. Or even the node energy. Some nodes simply are battery powered, where the other ones are electrically powered. So I make my decision based on those examples. Let's take a little scenario here. So let's say I have a very small ripple tree. So I have my root, and I have my 2 V6 sensor nodes that are already connected. And they're using ETX as their objective function. Now, they've already done the measurement, and they're already considering this as a 1, so it's a very reliable link ETX. Now, this guy comes along, and how many possible nodes could he connect to here? It's 3, right? He could connect to the guy on the left, the root, or the one on the right. So he does his probe, and he looks at the ETX value to each of them, and he discovers that there's a 1 on the left, a 3 to the middle, and a 1.5 on the right. The decision will be based on the sum of all of the ETXs back to the root. So in this case, the left-hand side is a 2, the one to the middle is a 3, even though that's only 1 hop, it's a very bad ETX, it's a 3, and here it will be 2.5. So his choice is going to be the link on the left, and he establishes him now as that position into the network. And that is his next hop to find his way to the root of this tree. Now, because this one on the right was a backup, it was actually quite good, he will keep him in his neighbor table as my alternate if this link were to fail for some reason. So that's a demonstration very simply of the routing process in Ripple. Now, let's take an example a little bit more complicated. Let's say we have this little node down here, and he wants to find his way up to the root, this connected grid router. Well, if we're going to use ETX, we'll just very simply go like that, because it's the lowest count of ETXs. But do you notice this node here? He's a battery-powered node. Well, why would I have a mix of battery and electrically powered nodes in the same network? Well, think about a power utility, right? A power meter has electricity running through it, so it's powered. But what if that same utility wants to bring on gas and water meters? Gas and water meters don't have electricity running into them, and yet they can form part of the same mesh and part of the same network. So now we've got battery nodes and electrically powered nodes mixed together. If I'm routing through a battery-powered node, what's going to happen over time? The battery is going to drain very, very fast. When we put these sensors out there, we want the battery to last 5, 10, if not 20 years before we have to go and replace it. If that battery drains in 3 months, this is not a good business decision, right? So we need to think about routing around that battery-powered node using a different objective function. So take this case. instead of using ETX, we'll say avoid the battery-powered node at all costs, but then use ETX as my secondary objective function. It lets me now route around that particular sensor, avoiding trouble and keeping his battery alive for as long as I need. Okay, so that's oh yeah, question here?
Question about security and trust.
Yeah. So the question is about security and trust? Yeah. So I didn't talk about it in this presentation, but it's in the book. But basically, as all these nodes come on, they use 802.1x, and they have a certificate. So they have to go through a very strict authentication and onboarding phase before they will be trusted. Only at that do we give them an address through DHCP and then start to build the routing topology. Good, thanks. Question?
However, the neighborship between the nodes is it's an unreliable network. So is it a protocol? It has to do with ETX calculation once a minute, or what is the schedule?
Okay, so very, very important question you asked. So the question is, because these are wireless networks and they're lossy networks, you could have a lot of shifting in the routing topology of this table. And that's one of the biggest problems that we have faced, to be honest with you. You know, a truck comes by and blocks the RF signal, and then the whole tree has to shift. Now, because these are not low latency type of systems, if this is reading a meter, for example, then we don't care so much if we can't read it for 15 minutes. But if we lose it for like 4 or 5 hours, that's a serious problem. So it really comes down to tuning and timing the network so that we have to build a stable mesh that doesn't move around all over the place. We'll typically find a primary parent and then a secondary parent. So you may have some movement between the two, but through tuning of the network, we want to keep that to a minimum. So transitory changes, we want to have as little as possible.
That's only true for a specific application in IoT. If you're talking about industrial IoT,
Yep.
I can't wait for a sensor in a temperature information.
Yeah. So the question is, what about industrial IoT? And I'm going to talk about that in a few minutes. So thank you for bringing that up. Okay. Now, one interesting problem with this is when you're dealing with big systems like smart cities or utilities, not everything is IPv6 capable. There's a lot of things out there that were put in 20 years ago that doesn't even have an IP address. And if it does have an IP address, it only is going to support IPv4. And you've built this big mesh of IPv6. How are you going to bring on these other types of devices onto this same network? That's a real problem. You want this to be one network, not lots of networks. For example, if we have little devices out here on our mesh that only support serial, how do I connect it in? Well, the answer is you use a gateway device. So Cisco has a product called the Industrial Router 500 series, which is really a gateway device. On one side, it's a mesh connection, so it forms itself as a ripple router. On the other side, it has a serial connection or an IPv4 connection. Well, if it's IPv4, how are we actually going to route through it? We've got a partial IPv4 domain, which is the endpoint here, and the application talking to it. And we've got a lot of IPv6 in the middle. It's really quite amazing. I'm always shocked when I work with manufacturing customers or utility customers, and how many devices that are sitting in their network that have the same IP address. It's like every single device is 192.168.1.1. And you're scratching your head, it was like, how did that happen? Well, they thought we'd never connect it, so we just left the default IP address and we shipped it out to the plant floor, or we put it up onto the poles or wherever it went. And now they want to connect them. And they don't want to send somebody and to reconfigure the addresses. So that means we have to go through a network address translation. Well, of course, for v4, we have to give it a routable address, but then we also have to bring it into the IPv6 world. And that's where technology called MAP-T comes in. So MAP-T is defined by RFC 7599, and it's really a stateless NAT64 technology, both for port and addresses, that allows you to tunnel through an IPv6 network an IPv4 application. Okay, so what we need is this gateway router here that supports MAP-T and a MAP-T border router. So let's look at the components between it. Our goal, let's say, is to do SCADA. So SCADA is a very common industrial protocol. We see it in almost every IoT industry. It's a way we have supervisory control to different types of devices. And I bet you most SCADA devices out there you'll see are not IPv6 compliant. And yet, we have this nice v6 network in the middle. So that's our goal, is to connect a v4 SCADA device from the application down to the endpoint. Well, in the middle, as we talked about, we have 6 low-pan here over the mesh, and IPv6 between our border router and that gateway. Well, we're going to have IPv4 natively on those 2 sections. So as you can see, there's going to be a double NAT situation. We're going to be NATing it from v4 to v6 here, and then a NAT 44 as we go from this same IP address, 192.168, to something that's more routable. The answer is we use MAP-T through the middle. So a little scenario here. So let's say we've got, this is our SCADA server of 10.1.0.60. And we're going to talk to this NAT44 address of 153.10.10.254. So how do we do this? Well, using MAP-T at the border router, we do a translation to hex. So we take our 10 address and the destination of 153, convert it to hex, and it goes directly into the IPv6 packet. So the addresses that you see here are a direct conversion of the decimal addresses of v4 into hex addresses here in IPv6. What this means is we're carrying the original IPv4 address as part of the IPv6 address. And we now transport it across the entire domain of IPv6 until it arrives over here at our gateway router. Now, he extracts the destination. He says, that's where you want to go. He has a NAT44 table and does a conversion and allows you now to communicate. And the result is I now have end-to-end IPv4 communication as an illusion through my IPv6 network. So NAT64 is a pretty hard thing to do sometimes, but MAP-T lets you do this at massive scale and allow these types of communication. What's cool about it is this big v6 network that we're building now is very flexible. It allows us to connect v4 objects that may not support v6 yet. We say, that's okay, we don't care, just put a little gateway router in. It's really small, and allows it to plug in as a native v6 type of transport. Okay, now let's look to the future a little bit. And the question came up about the reliability, I think, of the network. In factory situations, if you have automation and you have conveyor belts and robotic controls and a production line, this type of lossy network that might reconverge all the time is going to be very, very risky. And this is well understood in the industry. There's a very large class of IoT device where you cannot stand to have a lot of loss. Because if you do, the robotic control of an arm may malfunction, autonomous guided vehicle may fly off the road and cause an accident. These are real types of problems as more and more of these devices are being incorporated. So TSN is really about guaranteeing packet transmission time slots so that we don't encounter loss. So TSN is a very, very quickly emerging new technology, and it's not quite here yet across the industry. We see it in Ethernet, and there's a neat example at Wireless Solutions about Ethernet-based TSN. But TSN is also now emerging as an IoT standard. I'll talk about that in a few minutes. Now, this is a really cool truck. I wanted to buy one, but my wife wouldn't let me. Do you see anything that's strange about this truck? See who's paying attention. There's something missing. There's no driver cab. This is an autonomous guided vehicle. Right? This is a 100% sensor-driven vehicle built by Komatsu. This was taken at the Las Vegas mining show last year. Now, this is a pretty amazing thing. Would you trust running this type of a vehicle on a lossy network that reconverges all the time? I think that would be a very frightening thing. Where I live in Canada, our next province over is called Alberta. In northern Alberta, there is a mining company that's deploying 72 of these vehicles across their open pit mine. They're going to be running 24 hours a day, 7 days a week, and they're never going to stop. And guess what technology it's going to be using? Well, if you're going to be running this over cellular, you need to have cellular coverage. Well, up in mining communities, there's no cellular coverage, so you can't use a type of cellular network. What about Wi-Fi? Would you trust Wi-Fi that's a collision domain to run this type of system? Well, I mean, you could try to make it work if you don't have a lot of interference. But the answer is TSN, time-sensitive networking, where you schedule every packet transmission, and you don't have to worry about collisions, you don't have to worry about media access, random backoffs, and these types of things, which could cause a problem in autonomous guided vehicles. Now, we talked a lot about 802.15.4 as a Zigbee variant. It's one of the most commonly deployed technologies in IoT, and this is true in factories, in automation, in utilities, and smart cities. So TSN uses a variant called time-slotted channel hopping, where we have this hopping sequence that's constructed by a controller. So you're familiar with SDN controllers. Well, TSN uses the same thing, but it uses it to determine which radio gets to transmit and how many packets it gets to do it at any given time. So the entire network becomes very, very well structured and organized. Some companies have actually developed this technology in more of a closed way. It has been published, and there are vendors that are working with them. For example, Cisco works with Honeywell and Emerson, are two companies that build this type of TSN capability. Here's an example of one called ISA 100.11a. Up here you see there's a controller. So this device manager is really managing the transmission of this particular radio, these blue lines, to these factory devices. So if we have a programmable logic controller that's controlling the motor speed of something in a factory, for example, you better not be losing packets, right? Because that motor is going to run out of control and it's going to break things. And especially if you have a lot of conveyor belts and movement of objects and you're building something, you need to have determinism within that network. Well, that's what TSN is built to do. So these are Cisco outdoor wireless access points running a mesh. Now, what we've done is incorporated the ISA 111 radio into the Cisco access point. So even though we're running Cisco wireless here, this is a very stable 5.8 Wi-Fi connection. On the actual PLC-type connection that talks to the sensors, the actuators, and the motor controls, this is deterministic networking. This is TSN running between the PLC and these types of devices. And the cool thing about ISA 100.11a is it's all built on IPv6. So it's built to be an IPv6 protocol. Now, what we're seeing is a maturing and a development of this technology, and it's becoming something now called 6TiSCH. 6TiSCH is the IETF working group. They met 2 months ago in Singapore. It's very, very close to ratification. And this is going to change a lot of what we saw with Ripple and other types of mesh networking to bring much more of a deterministic structure so we don't run into those problems that you talked about of wireless collisions and dropping packets and these problems you typically would see on very large networks. What 6TiSCH is IPv6 time-slotted channel hopping. It brings all the components that we've discussed. 6LoWPAN, Ripple as a routing protocol, but adding a control element that schedules the transmission from each radio to make sure that it's much more structured and we're not losing a lot of packets. So this is a little bit more of a futuristic looking discussion, but it's really where we're going to see the industry head over the next couple of years. And even though we've got these very big networks already deployed, people are starting to want to put more time-sensitive applications onto them. So reading a meter is not a time-sensitive application, but a lot of other things are. Robotic control is, autonomous cars, those are time-sensitive. These will use a technology like 6TiSCH. Now, one last little story before we get into the case study. We've looked at a lot of the network architecture of how we can make IPv6 work better with IoT, and we can architect it in a certain way. But what about the management protocols? How do we manage all of these different sensors and devices in a new way? Well, along with the development of Ripple and 6LoWPAN, there's been development of management protocols. And one of them that's used a lot is called CoAP, the Constrained Application Protocol. CoAP looks and feels exactly like HTTP. So if you were to go to a browser and do HTTP : whack whack, it's very similar. It's CoAP : // and then you put in the sensor's IP address and you talk to it. Even the commands you use to talk to the sensors are exactly like HTTP. It's get, it's put, it's post. So if you're familiar with how HTTP works, you're going to be familiar with how CoAP works. But it was designed to take that knowledge and that structure, but make it much more efficient for lossy networks. And particularly, it uses UDP, right? So this is the big difference between HTTP and CoAP. It uses a small header, and it uses UDP. Now, with CoAP, let's say we wanted to talk to the lights in the ceiling. And by the way, the digital lighting vendors have all decided on CoAP as the network management protocol of choice. So let's say I've got these lights up in the ceiling, and I want to make a connection to my light because the light's a little bit too dim, so I want to make it brighter, right? So I go to my app on my phone, and I say, let's make this light brighter. So the app makes a CoAP call to the light using basically a post function. The light gets, do you like that animation? The light got brighter? So the light gets brighter, sends back an acknowledgement, a 200 OK, and says, yes, successful, the command has been executed. Even the message reply is a 200 OK. It looks exactly like HTTP, right? When you make a web connection through HTTP, it's a 200 OK message that comes back. Well, CoAP does exactly the same. Now, CoAP is nice because it's for constrained networks. It's in the title, Constrained Application Protocol. Constrained means low bandwidth, and you're losing a lot of packets because they're flapping up and down. that's the kind of environment that CoAP was designed for, and they're all IPv6 endpoints. The one disadvantage of CoAP is that you have to talk to every single device from a central location. So if I have 10 million sensors out there, one management station has to talk to every single one of them. Now, there may not be a way around that. That may be just the architecture of how it works, but that's sort of one of the fundamental issues with CoAP. An alternate technology is called MQTT, or Message Query Telemetry Transport. MQTT uses a very different concept. It's older, so it's TCP-based, so it doesn't work really well in constrained environments, because if you lose a TCP packet, it pauses, it retransmits, and goes through that process. But what MQTT brings is a publisher-subscriber architecture. So we don't have to talk to every single device. All we have to do is talk to a broker that sits in the middle. And the broker is like a proxy. So the broker will then talk to all the sensors, and all we have to do from a management station is talk to that MQTT broker. Now, take an example of a building management company. Let's say I have 1,000 sensors in a building, and I have 50 buildings. That'd be 50,000 sensors to talk to. And now, if I'm a network management station, does it really make sense from the cloud to talk to 50,000 different devices? Well, it's much better to talk to a proxy, or the broker, let him talk to those different devices, and I'll just communicate through him. So we use this publishing and subscribing model, where the sensors over here are publishing their IoT data, and as a subscriber at network management, all we have to do is pick something called a topic, which is what kind of IoT data we care about, and we'll start to subscribe to it, and we're going to pull it off. So this architecture works well in a lot of cases where we're not constrained. I want to show you this example that we're working on in Paris. So this is a building automation situation, and we've got a variety of different sensors here. We've got some lights, we've got temperature sensors, we've got distance sensors like ultrasonic sensors to see how far we are from a person or something that's in the building. We've put an Arduino device onto the network, and it's talking to these different sensors. And we have a USB connection to a Cisco fog router. Now, a Cisco fog router is a small little IoT router that runs a Linux container in Docker that lets you run pretty much any type of application you want. And in this case, we're running an MQTT broker that's open source called Mosquito. This is running an IPv6 network, so this is a v6 message broker. And we're subscribing to the information that's being published by these IoT sensors. So as they measure the temperature and the light, whatever, they're sending it over the Arduino up into the fog router, and they're being brokered here in Mosquito. Now, in the network management station below is our MQTT administrator. He's sort of curious to see what these IoT sensors are doing and what the temperature is. Maybe we want to change the lights in a room or something like that. So he is the subscriber. So we've got both a publisher and subscriber communicating over v6 towards each other. Now, here's my open source subscriber. He's running an application called MQTT Box, so it's a free-based application. We pick up an address through DHCP, and then he makes a connection to the broker. Now, as you can see, he's subscribing to topics. So one is our lights over here, one is our temperature, one is our humidity. Now, those topics are being generated by those different sensors and devices, sent to the broker, and then we're just pulling them back into the network management station. So this allows us now to, at a management layer, to get the information out of those types of sensors. I was over at DevNet yesterday, and they actually had a live working model of this, which I wasn't aware of until yesterday afternoon. So you can actually go to DevNet, developer.cisco.com, and you can try this out. You can actually build the Docker container, push it out through Kubernetes down to the Cisco fog router. It can talk to sensors. You can pull this data back and actually try this out yourself. So that's now on DevNet, which is pretty cool. Taking a sniffer trace here, we can see that here's our v6 addresses between the subscriber and the client, and here's the different topics that we're connecting to, and we're collecting this information back into the network management station. Right? So this pulls together the full package. Now, I just wanted to put this for your reference. These are the two most common network management protocols we see in IoT. There are some others, like XMPP, but these are the predominantly popular ones, and there are pros and cons to both, right? As we talked, CoAP is UDP-based, great for constrained networks, whereas MQTT is TCP-based. Whereas this, network management talks to everybody. There's no brokering. Whereas over here, we have a broker, which makes it a little simpler. Okay, so now I want to just wrap up and conclude talking about a case study. And this is the largest IoT deployment that Cisco has ever done. In fact, this is one of the largest IPv6 networks for IoT that's ever been deployed by anybody. And this was deployed in the city of Vancouver, Canada, which is a picture of it here. So this is my hometown. My house is not in this picture, but the Cisco office is right there, in that building. So that's where I work. That's in our office. We're very proud of our city. It's a very nice place. We have mountains and water nearby. But the power utility that delivers the power to the city and to the whole province needed to upgrade the infrastructure. They had very, very old 20th century system. A lot of the meters were actually almost 40 to 50 years old, and some of them were even rusted out. They had no way to measure the meter. They would just send the same bill to the customer every month. And the customer had no idea if it was true or not. They just had to pay, right? We have another problem in the place where I live, is that a lot of people grow marijuana. And now they're trying to make marijuana more legal, but they've had a problem because people steal power, and they'll put a marijuana grow operation into their backyard. And because they don't know how to properly bring the wires down, they'll burn their house down, and people are dying, and sometimes the transformers that are on the pole will explode, causing a lot of problems. So they saw there's a real business driver to replace the entire system with a smart metering system. Now, in total, this province has around 2 million meters. So the first plan was about 1.848 million. It's actually exceeded that now. We're over 2 million meters. The land area, though, is very, very large. The province of British Columbia is bigger than Spain, Portugal, and the entire UK combined. A huge land area, but the population is small. So it's around 4.5 million people, and there's around 2 million meters. There's another power utility which has some of the other meters. And the company that runs it is called BC Hydro. So they wanted to deploy smart meters throughout the entire province from top to bottom, including the large city of Vancouver, where more than half the population actually lives. Now, what they wanted to do wasn't just to build the same kind of smart meter network that everybody else had been doing for the last couple of years. They wanted to do something that was next generation. And this was about a multi-service, multi-application grid network. And this is a cool story because they wanted it to serve the electric vehicle recharging stations. They wanted to put the lights that they have 100,000 street lights. They wanted to bring those onto the network so they can have lighting control. They wanted to bring on other automation systems within their grid, things for the flow of electricity and the demand response, every type of thing you can imagine. They wanted to bring it onto one common network infrastructure. Well, you can't do that with traditional technologies that are proprietary based, that one application works on one network. The only way you can do this is an open network that's running on IPv6. It would allow all these different vendors that are building different product to simply use an open protocol stack. They can then plug it in, and then it will work on that same network. And the network we're talking about is exactly the discussion we've had. It's a Ripple-based network. It's using 6LoWPAN. We're using CoAP to talk to all of these endpoints. Now, BC Hydro was the first in the world. They're the first that have deployed a network like this on this type of a scale, but it wasn't the last. There has been many, many of these networks deployed all over the world, and it's growing very, very fast. But a lot of the lessons we learn and the technology that we've developed, which has become really the standard for IoT, IPv6 networking, was developed here with this customer. Now, the device they wanted to deploy is this one. This is an Itron smart meter. So this is a partner of BC Hydro. They had selected them as their metering vendor, and they had chosen Cisco to be the network provider. Now, Itron doesn't build networks, they build meters. So they had to work very closely with Cisco to develop the Ripple stack, the IPv6 6LoWPAN stack, and put it onto this meter. Now, if we can see in this meter, this board that's sitting behind is called the metrology board. This is what's actually taking measurements of the power and the phase and these types of things. We see there's a board here on the front. This is a Zigbee radio that talks to the home. So nowadays, you can actually have communications onto your dishwasher, your hot water heater, any appliance within your home. You can actually have communication from the meter, so there's communication in what we call the HAN, or the Home Automation Network. But this top board that's sitting at 90 degrees is the FAN board. This is the Field Area Network board, and this is what is running 802.15.4 with Ripple and 6LoWPAN. Now this board is running Cisco protocol stack on it. So every single one of these meters, even though it's not built by Cisco, has our software inside of it, and it's running that protocol stack that we developed 4 to 5 years ago. And what it allows you to do is now see how much power you're consuming. So instead of getting this bill from the company and you have no idea if it's accurate or not, they used to have teams of people, usually students from college, that would have to go out and read these meters, and they would only probably do it 2 to 3 times a year, and it was very inaccurate. Now, as a consumer, you can log in and see what your power consumption is any time of day. And you can get very granular. You can see even what different appliances within your home are drawing, and you can see in certain times of day how much you're being charged and different things like that. So it's a pretty powerful system. For those customers that are growing marijuana, it also made it pretty nice for the company because they don't have to send someone to turn off the power. All they have to do is from the network operations center, they say, well, there's a suspicion of a marijuana grow operation here, or that customer hasn't paid their bill in 6 months. All they have to do is press a button, and they turn off the power. Every one of those meters has a hardware-based relay that they can simply shut the power off and wait for them to pay the bill. So the network architecture looked like this. At the bottom, we have the meters, these 2 million meters, and they were formed into wireless mesh networks on 802.15.4. We have the home area network that sits below, but the grid router is the top of that DODAG tree, or that ripple tree, and below it were those meters. So there's an average about 1,000 meters per router. So that's a pretty big mesh. Now, if you look at the very dense populated areas like the city of Vancouver, we actually have up to 3,000 meters on a single mesh. When you get out to farm communities that are very far away, it could only be 200 to 300 meters that are connected in the system, but on average, it's around 1,000. And what we find is that the more meters you have, the better the network gets, because the more options for network connectivity and finding parents, that makes the network run just smoother and faster. Well, how do you connect this back? Well, you have options. You could do a WiMAX type connection back to the core, cellular, satellite in very, very remote communities. But the V6 network spans from here all the way through a tunnel into the data center, and all the applications that are talking to those devices are also IPv6. Those applications are typically dual stacked, so they're V4 on one side, but the other side down into the IoT network is where IPv6 lives. So how do you address something like this? Well, this was an interesting challenge. They needed IPv6 address space, and they needed, what they thought is a lot of it. Well, of course, with IPv6, addresses are plentiful. So in North America, we have ARIN, which is the American Registry for Internet Numbers. In Europe, you go to RIPE. They got their address block, and they got a /36. Now, from the /36, they thought, well, OK, we're building an IPv6 network for IoT, but you know what? We want to think long term. What if one day the entire enterprise network becomes IPv6, or the data center all becomes IPv6? We want to plan for that day, even though it's not going to happen right now. So what they decided to do is, let's take that /36 and break it into a whole bunch of /40s. That gives you 16 possible /40s, and we're going to divide it up for different parts of the network. For example, there's a /40 that went into the smart meter network. Those are the meshes that sit below. Every little mesh from the grid router below has a /64, which gives you like more addresses than you could ever possibly need. The standard limits you to only 1,000 meters in a mesh anyways, so this is plenty to use. We're going to use another /40 for the infrastructure side, so for loopbacks, for the tunnel endpoints, to bring their IPv6 network back. But then they thought, well, let's also reserve a /40 for future infrastructure. Let's put a /40 for data center, a /40 for the enterprise network, another one for the WAN. So this allows you to plan for the future without having to invest immediately in IPv6. And it's a good strategy. It gets you onto a roadmap without having to make a massive change all at once. So with that deployed, the network went in. And in apartment buildings, this is a meter vault. We would have a whole bunch of meters go in like this. When you see a picture like this, OK, question? Yeah, okay, so that's a good comment. He was talking about narrowband IoT. So with narrowband IoT, every mobile device has its own /64, which is a good point. And if you know IPv6, the smallest address space you can have is a /64, right? You cannot have a subnet smaller than that. So this model was not built with narrowband IoT in mind. This was designed probably 4 years ago now. So as technology matures and changes, we need to think about, is this enough address space? You know, at the time, it seemed like it's a lot. One thing about this /36 is ARIN in North America reserves another 4 bits. So even though they've bought a /36, there's another /32 that's actually sitting there available for future use, reserved for that customer. So they can always go back later and get more. But I like your point because IoT has changing in ways we never expected. And we're going to use more address space than we ever thought. So always go bigger, and don't go skinny. You know, think about possibly using it in the future. When you look at this, people think, that's meters. You know what I see when I see that? Those are IPv6 endpoints. More than that, those are IPv6 routers. Every one of them holds the routing table, is making routing decisions how to pass packets. So I like to tease my friends who are in the service provider space and ask this question, what's the most deployed routing protocol in the world? And people say, BGP, right? That's the most deployed. I say, well, no, I disagree. It's Ripple. By number of devices in production in the world today, Ripple is in tens of millions of devices, and it's growing faster than any other routing protocol. The difference with Ripple is that every endpoint isn't just an endpoint with the default gateway. It's actually holding a routing table and making decisions based on an objective function. So quite literally, Ripple is the most deployed routing protocol in the world. Now, when we deployed this, though, we worked very closely with this customer. We were developing this technology as they were pushing us to get it out. And the standards bodies were just starting to come together. RFC 6550 for Ripple was only just being formed. They needed to deploy it quickly to meet some government deadlines. So they worked with their partner, Itron. They put the whole network in with the Cisco grid routers. But at the first day, it only talked proprietary communication protocol. There was a proprietary mesh network that was put in. And when it was put in, you can see that some of the meters were 30 levels deep within this mesh. What do you think the performance is talking to a meter that's 30 levels deep? You almost never see it, right? You'll hear it from like once a month kind of thing. When we were ready, it took us about a year to get the IPv6 stack ready for all the meters. We pushed it out through a multicast. So we pushed it out to 2 million meters. And the software sat there on the meter until we're ready to make the conversion. And we would do around 250,000 meters at one sitting. So, you know, you'd press the button and everyone just like, you know, they're praying and they're holding their breath to see what happens. Is this actually going to work? Because it's never been done anywhere else in the world. And slowly the meters would come back after they rebooted themselves, and they would start to form a Ripple tree, and they would connect to the grid router. And it would take about a day or two, because it's a very, very large network. We'd be doing like 250,000 meters at a moment. And as it would come back, we start to see the tree was very different. The mesh network that was growing now based on IPv6 was a completely different structure to what had been used previously. And the new structure was so much faster. It was, on average, only 14 levels deep compared to 30 previously. The latency between hops was incredibly improved. If you look on the left-hand side, this is the latency between hops. To get to 5 levels deep, 5 ranks, it was around 11.3 seconds to talk to a meter that was 5 levels deep. That's a long time to wait for a ping. But that's what it was on a proprietary-based protocol. And this is what a lot of technologies had been deployed previously around the world. When we went to IPv6 and the mesh reformed itself through Ripple, to me, this was like a testament to the efficiency and the brilliance of this protocol, how well it worked, and why it is going to be successful. The average latency, it dropped so much that we could now get down to meters in a few seconds, and the mesh became so much more stable than it ever was. Now, a lot of this technology was developed around 4 years ago. We're now entering the second generation of this technology that's going to improve this performance 4 to 5 times faster than it even is today. And over time, we'll start to see capabilities like TSN come into this mesh where we're able to do time and latency sensitive applications where we won't have to worry about packet loss because of collisions and channel hopping and colliding at the same moment. It also allowed BC Hydro to capture their vision of making it a multi-service network, not just smart meters, thank you, of making it just smart meters, but they were able to bring on other types of applications. For example, this one is called the demand response controller. What's interesting in the power industry is that power always has to be perfectly in balance, right? Power being generated has to match power being used. If you produce too much power, you have to throw away power and you lose money. It's called power shedding. If you don't have enough power and people are consuming too much, you're gonna have a blackout. So what the industries are doing, companies are doing, is using demand response. So they'll talk to very, very greedy type devices within the grid, and they'll turn them off at peaking periods. So when everyone's coming home from work on a hot day, and they turn on the air conditioning unit or something, that consumes a lot of power. They can control that through a demand response controller. So this DR controller went in, and they were able to control these electrically powered water heaters, preventing them from controlling too much power. It also makes the grid really smart. You can now start to do machine learning on these devices to understand where the dynamics of flow and power and control them as you need to. It also allowed them to deploy streetlights, and this project is happening as we speak. So the streetlights, all they have to do is put a new module on the top of an existing streetlight, and they have connection to the light and the power usage, but guess what? Because every radio that goes on top is also now part of the Ripple network, it becomes a repeater, and it strengthens the mesh. And the position of a light on a street, it can talk down to homes. It's in a very natural position that makes the mesh even better and quicker. So that pretty much concludes the story of IoT and IPv6 as we know it today. And I think if we're to take away one message from this, we can see that IoT and IPv6 have kind of matured together. In a way, IoT has given a new life to IPv6, and it really is the only routing protocol and protocol of choice for networking when we look at the scales of these networks. If you're interested in learning more, I handed out 2 of those coupons. You can check into that video series. This Cisco Press book, which I was privileged to co-author, it's also available from Amazon or the Cisco store. It was published last summer in 2017, so it's very current, and we talk about all these kinds of things. Now, this is the end of Cisco Live, but you can also go back if you're interested in IPv6 and learn a lot more about some of these other technologies. But in conclusion, I just wanted to ask one favor, is to please don't forget to fill out your surveys. As speakers, this is incredibly important to us. It allows us to come back next year and improve the content and to enrich it. And I know everyone's going to be headed to the airport or go see some sites, but if you could just take a moment just at the end of the session to fill out the survey, we'd appreciate it very much. Thank you very much for coming. Hope you enjoyed the session. Enjoy your travels.